All right, so let's consider some examples and figure out how to solve them. Let's say we need to find the buoyant force on a cube of ice that measures 5 meters on each side. So we know it's ice, and also I didn't type it up, but let's say it's floating in water, where ice usually floats. So we have the density of ice, which is usually 917 kilograms over meters cubed. The density of fresh water is 1,000. So to give you 3 sig figs, that's 4 sig figs actually, that's how we're going to write it. And then since water is more dense than ice will float in water. So, and as you see, the density of ice is pretty close to water. So here comes your iceberg. Most of ice is going to be in. So most of the volume of ice is going to be inside water. By the way, what volume are we talking about? If this is a cube and it's 5 meters on each side, so it's going to be 5 cubed, which is 125 meters cubed. All right. So basically, the first question you already kind of asked yourself, is ice going to float in water? Since water is more dense than ice, then yes. So since ice floats in water, then we know for sure that the buoyant force in this case is going to equal the weight of that ice. So this is our weight of the object, and that's the buoyant force. So that's the case when an object floats, and mg equals buoyant force. All right. So as you see here, what I did is mass is density times volume times g, and that equals our buoyant force. So in this case, density of ice is 917, volume of ice I already showed you is 125, g is 981, so that is our weight of the object. This is mass right here, and that's g, and that equals this amount. That is the buoyant force, so we found it. Now what if we have another question and we need to find the part of volume that is in? So again, most of our ice is in, so we're going to try and figure out how much of that ice is inside. So this part of volume that I just highlighted right here or colored in, we're going to try to figure out how much of it is in. So that is the volume that we're going to be looking for. So as we established, the weight of the object will equal, so technically if I were to write it as we had it before, the weight of the fluid, which is buoyancy force, equals the weight of the object. And then since these g are identical, we can just get rid of them. So the mass of the fluid equals mass of the object, which I can rewrite as density times volume and just rewrite it with each subscript. Since this is fluid, that would be density of the fluid times volume of the fluid. Object will have density of the object times volume of the object. And then the amount of displaced fluid will equal the volume that is inside water. Because again, if this is our cube, this amount is underwater. That is the amount of displaced fluid, and that is the amount of water, the amount of ice that we're looking for, the one that's underwater. So in this case, all I do is I rewrote the formula above right here. So we're looking for volume of the fluid, which equals the volume of the submerged object. So right here, I take the right side and I divide it by density of the fluid, which in this case will be 917. That's the density of ice, because that's our object, times 125. And all that divided by, since it's water, 1,000. So there we go, 115 meters. And if you compare, the whole thing is 125 and 115, and that's meters cubed and meters cubed in each case. Only 10 cubic meters are above. The rest of it is in. That's why icebergs are so dangerous. What if we were asked to figure out the apparent weight of this chunk of ice that's in water? As you remember, apparent weight is mg minus buoyant force. And since it's a floating object, then mg equals buoyant force, which will amount apparent weight to 0. So objects that float do not have any apparent weight. Their apparent weight is 0. What if an object does have apparent weight? And in this case, we have an object measuring to 45 newtons when it's in the air, so that's the actual weight. And then when it's weighed in oil, the weight appears to be 35 newtons. We need to find the density of the object. This resembles your lab. In your lab, you're measuring the actual weight in the air, and then you measure their apparent weight in water. In this case, this is oil. But the technique and the steps are identical. So let's say if an object has apparent weight, then obviously it sinks. Because when we weigh something, so let's say this is our indication of 35 newtons, which means that our object has 45 newtons of actual weight going down, some normal force, some buoyant force, I apologize, some buoyant force going up, and our scales are showing 35 newtons. So you can basically figure out that the buoyant force here is going to be the difference between 45 and 35, and it's going to be 10 newtons. So this oil is producing an upward push that equals 10 newtons. That's why the object appears to be only 35 newtons in oil versus 45 newtons of its actual weight. All right, so we have the actual weight of 45 newtons. We have the apparent weight of 35 newtons. We have, it's going to be in your data when you solve a problem like this. The density of the fluid, which is oil, is 802 kilograms over meters cubed, and we need to figure out the density of the object. So, since our object has apparent weight,